class, we are now on 16.4. We're going to look at expressing the equilibrium constant in terms of pressure. Up to this point, we were looking at molarity, concentration, but now we're going to look at pressure. Okay, so we're going to look at equilibrium constants for gaseous reactions by looking at the partial pressures of a particular gas in that reaction. That is also, by looking at the partial pressure, it's also proportional to its concentration. So we're going to move off concentration and start looking at partial pressure. So in this case, therefore, the equilibrium constant can be expressed as a ratio of the partial pressures of the gas. So if we set up the law of mass action, but now we're going to change it over to partial pressure. So here's our general equation. And remember, the A, the B, the C, the small letters are raised up to the power. We take the coefficients and raise them up to the power for that specific reactant or product. So now we're also going to use a C and a P. C, when we're dealing specifically with concentration, which is molarity, and P for the partial pressure. So P is representative. So you need to make sure of which one you're also being asked to look at. So what this means in this case is PA is the partial pressure of A, PB is the partial pressure of B, and so forth. And then as you see, if we have an A, we raise it up to that power, B to raise it up to that power, and so forth. You also need to understand that when we start using Kc and Kp, the numerical value is different than the numerical value of Kp. So we're going to actually have to do some adjustments to make sure that we can transfer between Kc, the equilibrium constant. When I say Kc, understand I mean equilibrium constant for concentration, or Kp, which is the equilibrium constant for partial pressure. It's just easier to say Kc or Kp. But they are not equivalent. We're going to have to use a formula in order to be able to transfer or intertransfer between, or if you want to say interconvert, between these two. So here, if you recall from the ideal gas law, we have PV equals nRT. So if we rearrange this, concentration is moles over volume. So this would be molarity right here. So if we can substitute and move everything over, so if we isolate the moles over volume, we have now it's equal to the pressure over the gas constant times temperature, which is always in kelvins when we're doing these, because remember, when we deal with gases, we deal with kelvins. So N is mole of A, for instance, if we used A, and V is the volume of gas. So we can rewrite this. So instead of using the concentration, which is what we would represent as concentration molarity is moles over volume, we can plug in, because that's what this would be, we can plug in the pressure over the gas constant T. So this is what you're seeing here. And now we use parentheses instead of concentration brackets. And we still raise everything by its coefficient to the power. Okay, so we rewrite the general equilibrium constant for concentration. We substitute pressure over the gas constant and temperature for the molarity of all the species in the reaction. All right, so an equilibrium constant expression can be written in either terms of molar concentration, which is Kc, or in terms of partial pressure. So you got to make sure you understand which one is being asked, and in some cases they may even ask for both. So this is the law of mass action. We can write this out. Here's our equation. We can take that information and write that out here for molar concentration of the reactants and products. We can also write that in terms of partial pressure. And if you notice, we're still raising the same coefficients up. So the only difference really is that we're using P and we're moving the concentration brackets with the parentheses. I mean, it's a little more complicated than that, but writing it out, there's really not much difference here. So here is a general equation, a general balanced equation, and then we can write the partial pressure, the law of mass action for the partial pressure of each reactant and product in it. Okay, so when we're going, the difference between Kc and Kp, well, one is in units of molarity. So Kc is in units of molarity, moles over liters, and Kp is in units of atmosphere, ATM, and its pressure. So they do not match up. We need to actually be able to use a formula in order to go across whichever one we need to solve for. So in this case, here is what we're going to use, this formula. So the values of Kp and Kc are not necessarily the same because they're two different units. So you could not convert them. We need something in order to do this. So this is the formula we're going to use. So we have our equilibrium constant and partial pressures on one side, and it's equal to the equilibrium constant of molar concentration, and we have a parentheses of our gas constant and temperature, which is in kelvins, to the power of delta N. So what is delta N? We're gonna, there's the next slide, I'm gonna show you what all this is. But delta N is the difference between the number of moles of gaseous products and moles of gaseous reactants. So I have it right here. We subtract the products, we subtract the reactants from the products, and that will give us a number. Now, we'll go on with this number later. However, Kp and Kc are equal when delta N is equal to 0. So what does that mean? Well, if you have the total number of reactants and you subtract the total number of reactants from product, and you end up with a 0. So if it's 1 minus 1, then it's 0. So if we were to take a look at something like this, we add up all the reactants and we add up all the products. So in this case, we would take 2 minus 3 because the reactants are after. So 2 minus 3 based on looking at this here. So it's 2 minus 3, and that would be a negative 1, which would make it the inverse. But I have an example to show you how to use this problem. So make sure you understand that it's simple. The delta N is just adding the sum of the reactants and the sum of the products, and you subtract the reactants from the products. That's what delta N is. And if they equal 0, then the equilibrium constant for partial pressure is equal to the equilibrium constant of molarity, or concentration. And this is just a long way of showing how this relationship works. So if we substitute the concentration of X for each one of these, so wherever we have the brackets, we plug in for the partial pressure. So that's what you're seeing here from this general reaction. Now we pull out the 1 over my RT. So now this is algebra, which not everybody can remember some of the things done in algebra, and that's what makes a lot of these things complicated. It's not necessarily the chemistry, it's the algebra. So we pull that out, and that leaves us with our partial pressures and raised to their power. So remember, up here, we are adding the products together. So this is where the C plus D comes in, because that is delta N, but we're breaking it down right now in between the reactants and products. So it's not the total. This is the total. This is the delta N right here, but we have to show how we got that. And the same thing here. We're adding the reactants together. That's the A plus B. But then we will subtract the reactants from the products, and that is representative of the delta N. So you can see it all rearranges and spells it out here. If you get confused, this is a good slide to look at and see how this is, how we calculated this or derived this equation. This is the same. This is just another slide showing the exact same thing, but it's just a little cleaner than that one. So either one, whichever works for you, but they say the same thing. Okay, so let's look at an example. The reaction below has an equilibrium constant for concentration is equal to 1.2 times 10 to the negative 4 at 1000 degrees Celsius. First of all, you should, not that that's related to this section, but you should start looking at it and getting comfortable with understanding numerical values. That is a number that's less than 1. So that means that this equilibrium reaction favors the reactants more than the products, because that number is less than 1. Okay, so now it's asking us to calculate the partial pressure, the equilibrium constant of partial pressure. So let's plug all that in. We need this formula that's going to allow us to convert, because we only have Kc, but we need Kp. So we're going to plug in this information. So the first thing we need to do is convert the temperature. We use kelvins when dealing with gases. So we end up having, and there's the final answer right there. You can see it. Now we need to determine delta N. So we have 2 moles of the gaseous product, and we have 1 mole of the gaseous reactant. So 2 minus 1 equals 1. So that's what we're going to plug in with 1. And you can see it right there. So here is Kc. So that's Kc. The gas constant is right here. And then we have delta T, which is Kelvin. And then we have brackets that represent just this RT in itself with delta N, which is 1. So we plug all this in our calculator, and our equilibrium constant for partial pressure is 1.3 times 10 to the negative 2. All right, so under which circumstances are Kp and Kc equal for the reaction shown here? So let's read these first of all. If A plus B equals C plus D, would that work? B is if the reaction is reversible, and C is if the equilibrium constant is small. B and C have nothing to do with this, because first it's an equilibrium. We're not concerned about the concentrations, the constant, because it's still an equilibrium. We are more interested in being able to make the equilibrium constant of concentration and the equilibrium constant of partial pressure equal to each other. That is just simply adding all the reactants up and all of the products up and then subtracting. So in order for that to equal, they would have to have the same number on this side as the same number on that side. So it would be A. And then if you needed to look at the reaction, the formula again, there it is. Okay, so some review. For the general reaction, which is shown here, the equilibrium constant for concentration has the form of the law of mass action. The brackets are representative of the concentration, which is representative of molarity. The reactions in the gas phase, the equilibrium constant of partial pressure is expressed in terms of partial pressure, and it is in atmospheres. For a gaseous reaction, if you needed to convert between Kp and Kc, we have a formula for that, and you need to plug everything in, R being the gas constant, T is in kelvins because we're dealing with gas, and delta N is simply summing up the moles of the products, subtracting the sum of the moles of the reactants, and that will give you your number. So delta N is the change in the number of gas. Species that are not solid, are in solid or pure liquid form phase, are not included in equilibrium expressions, so we still do not include them.